discover what happens with these groups, right? Like why are squirrels and fruit bats related? I mean, in what way are they even similar? Okay, so first thing that I will do, so yeah, okay. So now I can, well, change this connection if I want to. It's not strictly necessary. So now I'm not using this selected data here, but just I will output everything, like all the clusters. But this is not super essential because you will get all the information anyway. So now I have 4 clusters. And let's see how I can describe them. So now I will say, okay, split by cluster and, okay, order by relevance to subgroups as before. So now we're going to explore what each cluster is defined by. And here I see that clusters correspond very well to types. So before we saw that each animal is described with some features and also the type, like the family, animal family it belongs to. And you can see that clusters correspond very well to animal types. So cluster C1 is the cluster of mammals. Cluster C2 is the cluster of birds. C3 are fish. And C4 is very mixed. We got some amphibians, insects, invertebrate, and reptiles. And here we see that in the bird cluster, there are some, like 5% of reptiles that, I mean, they kind of strangely belong there. It's we don't know what happened. But great thing, I can click on this square and just briefly inspect what is the reason. So now I got tortoise, which is a reptile, but it got together with birds. So it's in the cluster with birds. Any idea why?
Maybe because it has the same features as fish.
Eggs, for example.
Eggs, yeah. So my guess would be eggs, right? Because tortoise also lays eggs, and so do birds. And that's easy enough to inspect, actually. So here I know that they're in cluster C2, so I just select this cluster. Here I will have to do the reconnecting again. So now I want to see data to data. Oh, actually, sorry. My mistake. Here I need to fix the connection. So idea is that I want to compare C1 to all the other data points. So now only the animals that I have selected here in the visualization are in C1, and they have selected yes, and all the rest are selected no. So you see that this corresponds very well to what I had before. And okay, so the defining feature of cluster C1 is feathers, and most of the animals actually have feathers. I would assume that the tortoise is the only one that doesn't have feathers. Okay, legs again. So, okay, one thing, it doesn't have teeth. So that's a thing that quite well defines cluster C1. So the tortoise is there with birds because it doesn't have teeth, apparently. And it also doesn't have hair. Eggs, okay, again, this is pretty simple. Do you know why X is not higher up? So we assumed that Okay, both birds and tortoise lay eggs, but why is it not higher in the list?
Because there are so many other animals that lay eggs.
Perfect, yes, exactly, because it doesn't split between the groups. So here, selected group, I mean, our birds all lay eggs, but so do some other animals in the non-selected group. I would say it's the insects, right? Insects also lay eggs. So yeah, but this seems to be a part of the reason why tortoise is in the bird group. Okay, perfect. So this is the way to explore all of these clusters. Let's try this one because so squirrels, fruit bats, and vampires are apparently all mammals, and a reason why they belong to C1. And they all give milk. So squirrels, fruit bats, and vampires all give milk. So that's why, even though at the first glance it looks strange, but that's why they're together. Maybe you want to target specifically these three animals. Let's see. Okay, it's the milk. They have 2 legs. They do not lay eggs. And they're hairy. So if you want to answer the question, okay, why are squirrels, fruit bats, and vampires in this subcluster? This is how you do it, right? Select it in the visualization, connect the data output to box plot, split by selected, and then just observe the importance of variables. Okay, any question regarding this data cluster exploration task? Okay, if not, let's just go a step further. We still have some time left. So now, you know, we saw, so how do I even, I have trouble visualizing this data set because it's all categorical data. But now I can only observe two variables at once in this box plot, right? So I can see, okay, I can split by some categorical variable, let's say selected, and then I can observe the variable here. Same in scatter plot, right? So even if I look at the dendrogram, I have no way of knowing how close is, let's say, the squirrel to the chicken. I do not know, because I mean, I can go, like, I can travel along this tree and up and then here, and then I would get to the squirrel, but it doesn't really tell me how close is the squirrel to any other animal apart from, let's say, maybe fruit bat and vampire. So ideally, I would like to find some visualization that would put all the animals on a map where similar animals would be placed close together, right? And these similar animals would be far apart. And there's a visualization that does exactly that. And it's called MDS. So MDS is short for multidimensional scaling. It's a fancy name for basically a data projection technique which puts multidimensional data and tries to fit it into 2-dimensional space. Okay, let's observe MDS, because so now I will go, let's say, with 4 clusters, and this is MDS. I will also label my data points. So here there's a little bit of an issue, right? Because as you saw here in the dendrogram, some animals have the exact same values of attributes. So that's the vertical line here. So this means that these animals they're the same based on this data set. So also here they will overlap, right? Because I mean, they're so similar, they would be in the same position. So what I can do to help me with this is something called jittering, which is an artificial, so I artificially push the data apart a bit. So this is just, now I won't have the exact position, but I will just push them apart in order to see them better, okay? So now this map is not like 100% right, let's say, but this will enable me to read all the labels that I have. Okay, so MDS, as I said, what it does, it puts animals that are similar close together and pushes animals that are different further apart. Now you have to understand here that we're not talking about two-dimensional data anymore, like with grades. So with grades, we had two attributes. We had English and algebra, and it was easy, right? We could plot it and we could visualize it. Here we have, I think, 32. Oh, okay, 17, sorry. Yeah, okay, so 17 variables in this data set. But this means this is 17-dimensional space. So each feature, each variable is a dimension. And each animal has some value in this dimension, right? So the number of legs, or it has milk or doesn't, and so on. And now I have to squeeze this 16-dimensional data and put it in, like squeeze it into this 2D space. So inevitably, this will not be exact. So this visualization is not an exact representation of the data, but it's an approximation. I can actually show you how this happens. Okay, so now I'm just kind of randomly putting, okay, let's randomly put the data. Okay, so now I randomly put animals all over the plot. And I will refresh the visualization at every iteration, and you will see what happens, hopefully. Oh, no. Okay, apparently something went wrong. Let's try it again. I hope. Oh, come on. Okay, apparently orange is a bit broken here. Sorry, I wanted to show you, yeah, how MDS optimizes this projection, but apparently this doesn't work. Probably it works for you if you're on older versions of Orange. If you have the latest version, we need to fix this. But essentially, so it doesn't start randomly. It uses something that Blaž will tell you about tomorrow. It's called PCA. And then it kind of drags these instances, these points around the map, and to model these distances as veritably as possible. But as I said, some mistakes happen. So you will see that now, like tortoise here. Okay, so I will just unjitter this a bit because this will be a more exact representation. So tortoise here, okay, not just tortoise, actually all of the C2, the entire C2 cluster, which are the birds, and well, the tortoise, are kind of, they fell in between this cluster of like C4 cluster. So you will see the line that connects, like I think housefly and gnat, the line here. So this is the option here that you see, show similar pairs, because this is a projection, so like an approximation. It won't be exact, as I say, and show similar pairs enables you to see which instances are actually should be closer than they appear in the map. So this housefly here and gnat here, they should be closer, but these birds, the C2 cluster kind of, because we couldn't properly place it into this space, it kind of got in between these C4 animals. Okay, one nice thing that I can do is I can do this. So I'm not sure Blaž showed you this. I think he didn't. So in MDS and in scatterplot, you can color the regions. So you see now, this is the region of cluster C1. This is C4 mostly, and here is C2, and at the top is C3. Okay, and the great thing here is that I can see that the tortoise, which was like, it was an outlier, right? In hierarchical class, I mean, we saw in box plot, right? That C2 was a little strange. It had this one outlier, which was tortoise, and you see here that it's not, you know, it's a bit outside of the group of birds. So birds they're closer together here, and tortoise is, you know, traveling kind of towards these other animals. I can try and color by type instead. So you will see now that the tortoise is actually a reptile, and it's closer to this group of reptiles. But in clustering, it got clustered with birds together. And then there's one other outlier, and it's this sea snake, right? Any idea why sea snake is here?
Because it is aquatic.
Exactly, right? So it does, I mean, this clustering, what I'm trying to say is that it even though, I mean, the result might be a little strange, it tells us a perspective on the data. So even though sea snake is biologically a reptile, it's aquatic and it lives in the water, so it's no wonder why it's close to fish as well. So whenever, I mean, clustering, even though it's inexact, it can tell us a lot of interesting things, right? About the data. And this is also nice to see. So we can see that sea snake, I mean, originally it's a reptile, but it got clustered with fish, and we can use boxplot to explore why this is the case. And my favorite also is here. So this porpoise and dolphin in this section, they're, you know, traveling to the, like the north of the visualization to the top. Why? Again, they're mammals biologically, but they also live in the water, so they're aquatic and they're put close together to fish. So is platypus, so is the seal and sea lion. So it makes sense why these mammals are close to fish, because they're aquatic, right? So this is the beauty of MDS. It will show you the structure of the data as well as it can. Okay, some questions? So if there are no questions, maybe I can touch upon the topic that Blaž will discuss a bit more tomorrow. And this is, so in clustering, how do we estimate? Oh, is there a, there's something in chat. Let me just, okay, nothing major. So in clusters, how do I know if a data instance is, like, for example, here in MDS, C-snake is an outlier in this, let's say, fish cluster. How would I determine that I have an outlier? Or how would I say, you know, is clustering any good? Is this, does this clustering make sense? And this number of clusters? Okay, ooh. Oh, come on. Okay, so let's say I have 4 clusters, and now my objective is to determine if these clusters are okay. Okay, that would be the easiest way to put it. And I will use something called silhouette plot. So I won't go deep into what silhouette is. This is something Blaž will explain tomorrow. But essentially, we are able to observe any kind of categorical variable and see how well the data instance fits to that categorical variable. And fits, I mean, based on the Euclidean distance. I will just say for now that this means that silhouette plot means how embedded the data instance is in the cluster. Okay, if it's in the center of the cluster, it will have a high silhouette score. If it's at the border of the cluster, it will have a low or negative silhouette score. And here, what I have is the cluster label. So not type, but let's say cluster. We had 4 clusters here. And you will see, okay, I will just increase this a bit. Okay, maybe just increase it all the way. So in C1, the most representative instance of C1, well, they're wolf, puma, boar, cheetah, and so on. So these are typical C1 representatives. And the ones that are, so here is the 0, and with those instances with negative scores are, let's say, outliers, are not representative of C1. And these are unsurprisingly dolphin and porpoise. So porpoise is like kind of a seal, narwhal kind of thing, I believe. And as we saw also in NDS, they're on the border of their mammal cluster. So these are untypical mammals, and it's true, dolphin is not a typical mammal, while wolf kind of is, right? And it's the same for all the rest. So here in C2, you would see that tortoise has the lowest silhouette score. And here in C4, you would see that, you know, quite many. So sea snake is completely untypical for C4. And also, well, all the instances here. So perhaps this is an indication that C4 is not the best cluster. So C1 is kind of okay, but these two, C2 is okay, C3 is really nice, and then this one has some negative scores here. So perhaps I need to rethink the number of clusters. And I can do this very easily. I can just, let's say 3. Okay, the scores got a little better. Or maybe I can even, just increase it to 5, let's say, and see what happens. So this allows me to explore my data set. So yeah, C1 remains the same. Dolphin and porpoise are here with negative score, and then C4 got split into C4 and C5, and this is a little better, and this is, well, it still has the sea snake that we mentioned is on the edge of, it's kind of, well, not very typical for the cluster. And another benefit of silhouette plot is that I cannot only explore clusters. So with this I can explore clusters, typical representatives, and outliers in clusters. But I can explore any categorical value. So I can say type, because we know the type of animals, and I can observe typical amphibians, typical birds, typical fish, invertebrate, and so on. Okay, here you see that even with this like official biological label, slug is an untypical vertebrate. So here you would see less typical representatives of this group. Of course, less typical based on the data that we have, right? So it always depends on the data. And again, here, same thing again, dolphin and porpoise are untypical mammals.
What are the values on x-axis?
You mean here?
Yes.
Okay, yeah, good question. This is the silhouette score. I do not wish to go into too many details because Blaž will talk about it tomorrow, and he will tell you how the score is computed, what it means in clustering, and you will work a lot with silhouette score later. But this is essentially the score, and the higher it is, the better. Okay, so I mean, the higher it is, the more central the data point is in the cluster. So that is the that is what the score reflects. Okay, so any questions or concerns, or did I not explain something well enough?
Well, obviously, it's quite clear. No one asks anything else.
Okay, so I'm quite finished with hierarchical clustering as a topic, but since we have half an hour, I thought perhaps we can just check what we discussed a bit earlier, the linkage, just play around with it for like 15 minutes or so.
Okay, okay.
And then maybe we can call it a day. Here, so now you don't need to follow, just just look at what I'm doing. So here I have some clustering data, and I will show you how it looks like, and maybe we will try to determine what kind of linkage is the best for this this task. So I'm loading clustering 1, and it looks like this. Okay. I am quite sure that you can think of that you can imagine how many clusters there are. And now I will use Euclidean distance again. So this is standard. And in hierarchical clustering, I will I can just go through all the linkages. Okay, so here I will set selection top 2. Why will I do this? What does this mean? This just means give me 2 clusters. And you can see that now the cutoff is at 2 clusters. So selection top n2 means just give me 2 clusters from this dendrogram. And this is because here I know that I can see that I have 2 groups. So now the question is, how well does this linkage perform? Okay, maybe I will just hide this and expand this one. Okay, so you tell me which linkage is the worst performing for this data. Okay, so this is single, average, okay, weighted, complete, and word. So which one was the worst?
Complete.
Exactly. Yes. So complete didn't work well on this data. So here it's red, and it's also red in the lower part of the big group. Why? So I will repeat. So complete linkage joins data instances with the smallest distance to the furthest instance in the group. Okay, did I say this right? So it looks at all the other groups, and it will take the group that is the closest to the existing group, judging by the instance that is the furthest apart in the group. So why doesn't this work? We can try and observe it here, right? So how, okay, this will just slowly show you, okay, here. Okay, so now C6, the pink group, is already together. Still one group, still one group. Okay, so now it's here. You can see that this group is so large that like the perimeter of the group is too big. And now the perimeter of this group is bigger than the distance between these 2 groups. So this is why at the final stage, they will get joined together. Because the distance between, so for example, if I take this instance here to the furthest, so here to the furthest instance here is shorter than from here to, let's say, the furthest distance instance here. And this is why these 2 will get together in the end. So like this.
But when would then use complete?
Basically, when you have smaller compact clusters. So if you have these large spread out clusters, it doesn't work well. But if you have these tight clusters, it would work. We will see with next examples maybe. So let's try the second data set, which is like this. So judging by the image, which clustering would work best. We had something similar before.
Single?
Single, exactly. I was talking about slugs and this kind of connected shapes. Let's try it. Okay, so I have to select 2. And single indeed successfully recognizes these connected shapes. So the space between these 2 shapes is quite big, but they're not circular. So this is where single really works well. And you will see that average, weighted, complete, and word all fail. So this is a case for single linkage. Okay, let's try clustering 3. It's like this, a bit similar than before, but not too similar. So here, this is a little tricky. Single, we see that it completely fails. And by the way, this is a typical structure of a single linkage dendrogram. So it just goes into it grows into this one top level tree. Okay, this is average. This works okay. Weighted doesn't work. Or complete or word. So the only one that works here is average. Which to me is quite surprising, but it's the case. And finally, you have clustering, the 4th one. And it's again one big group, and then you have 2 smaller clusters. Single is again a big fail. Average is also doesn't work. Weighted, complete, and word. And here, so here you will see why word is the best. I mean, the best. Again, the choice of linkage always depends on the data type. Different data will, each data set will work better with a different linkage, as you saw. And here word works best because it optimizes, let's say, the compactness of clusters. So this is compact, and this is kind of like everything else that's not in these compact clusters. Of course, here you would probably prefer free clusters, and Word is also able to find this very well. Okay, so this is just a little short demonstration how different shapes of data affect the choice of linkage, or vice versa, how linkage is reflected in clustering of different data types. So now if you have questions, this is the perfect time to ask. You will talk tomorrow with Blaž how to evaluate a good number of clusters. He will show you some another clustering technique that overcomes some limitations of hierarchical clustering. And he will show you projections. So we saw one today, which is MDS. So he will talk a bit more about MDS, and he will show you two other projections, which are really great because you can see the data on a plot. And in the afternoon, we will do some assignments. So we will do an assignment on data visualization and an assignment on clustering. And we will be using archaeological data sets. So this is, today we just use general data sets, but tomorrow we will work with some pottery, and on Wednesday we will use images of amphorae. So we will dig into archaeology as well, pun intended. Okay, any questions?
Yeah, now when we look at this plot we have right now, when I see the difference between C3 and C1 group, there are a few points which for me don't make sense being in the C1 group. So is there, I don't know if you see what I'm speaking about, but yeah, they're near your pointer. So yeah, those two. Yeah. So is there any possible way that like I can, based on my personal opinion or on my intuition, add them to a C3 group, or is it allowed or possible?
Interesting. Well, no, well, there is no manual way to do this, because this, I mean, a thing that you, I mean, here this is a little like, it's not cheating, but it's misleading. So your data will almost never be as simple as that, right? So you will, any kind of data set that you have will almost surely never be two-dimensional. I mean, it's almost impossible, right? Just, okay, let's, like, if I open quickly this pottery data that Pretnar sent me, or maybe it was Dimitri. So here already you have, you know, several columns, several dimensions already, right? So you will almost never be able to plot the data in 2D and say, okay, these two I would rather have with this group. So that's why it's not possible, because I mean, it would be useless for real life. This is simple because it's for educational purpose. You can only affect how these two are treated with the choice of distance measures and with the choice of linkages. So perhaps you can try different distance measure. We will use cosine later, and this will give completely different results because it measures distances in a different way. Okay, this won't work. Yeah, so you see that the way you measure similarity between instances affects greatly the results. And of course, as I said, the linkage. And we are used to thinking in two-dimensional terms, maybe three, okay, and in Euclidean spaces. So you would say, okay, this one is close to here. And for this data set, this would be right. But word linkage optimizes the compactness. So that's why it considered this green cluster compact enough. So it said, okay, this is compact, and this one, I don't know, it should be more in the blue section. So this is, yeah, just mathematics, how this word linkage works. So yeah, manually doing this would kind of defeat the purpose of machine learning, because it's meant to do things for you. And also in real life, yeah, you would not have a data set as simple as this one. But a nice way of just checking if this is really something that you want is, as we mentioned, silhouette plot. And then you can see, okay, this, okay, ooh, we know how to. So let's take this, yeah, the most uncharacteristic blue instances, and I can observe them in the plot, and they are as where you think they would be. So the border cases here. So you can identify these instances if it's not possible to see them in a map into this space. You can use silhouette plot and see, okay, these are the ones that perhaps should not really be in the blue group. Okay, I hope I answered this.
Yeah, of course you did.
Yeah.
I guess my brain just still works in 2D rather than like 17D.
Yeah, good or bad news, don't feel bad about yourself. Our brain cannot work in 17D ever. So, I mean, maybe some quantum physicists have this supernatural ability, but we're always thinking in 2D space and Euclidean spaces. So some results in data mining, if you look at them, will not be intuitive, but we will try to present some ways of thinking about the data and to see how to deal with, how to inspect unintuitive results and see whether really they're wrong or they're correct, but it's our intuition that is tricking us and so on.